Thank you all for being here. The title of my talk is Bias Introduced by True Radiation Patterns in Received Signal Strength-Based Visible Light Positioning. My name is Nobby. I'm working as a professor at the Faculty of Engineering Technology of the KU Leuven in Belgium. Now, shortly before I started this presentation, I realized in fact that not everyone in the audience was aware of the exact technology of received signal strength based visible light positioning. And in short, the idea is as follows. You're using the majority of the indoor premises have luminaires based on LEDs, and what you're actually doing is modulating the light, and with a dedicated device, which may be a camera or a photodiode, depending on the signal strength that you're receiving from each LED, you know where you are inside the indoor premises. That's in a nutshell where it's all about. Okay. Now, another thing that you might have heard before, but I want to remind you where it's exactly about concerning the difference between accuracy versus precision. There are two important properties regarding measurement comparing to the ground truth. So the left one is a technology you don't want to use, namely it's not precise, it's not accurate. The second one is very precise, meaning that the spread on the measurement result is very small, but there's a significant bias with regard to the ground truth, so it's not accurate. The third one is not precise, so a large spread, but the expectation value is close to the real value, to your ground truth. And of course, the right one is the technology what you want to use in order to have a good estimate of your ground truth. Now, if you take a look at the current state of the art of RSS-based visible light positioning, then it seems, or the technology is very precise. So the spread on the measurement is very small. This is proven theoretically by the Kramer-Rao lower bound, and we have also demonstrated it practically. So at a certain location, we repeat the measurements all the time, and then we calculate the spread on the results, and it's very small. Problem is, though, that the accuracy is challenging. Now, what we were looking for is a means, what is the real root cause of the limited accuracy? And so we identified the first one, namely the tilting of the receiver and or transmitter. So at the top you can see there's a transmitter and the photodiode is at the bottom right, and you can understand, for instance, if an LED is attached to a ceiling, high ceiling of 6 meters high, and it's slightly tilted even over 1 degree, which is very little, that the impact on the distribution of the signal strength at your observation plane can lead to errors which are easily within 10-15 centimeters. Okay, so we elaborated that theoretically, and the next step was that we could be, if we have an LED at the ceiling, that we introduce a certain tilt, and that by measuring at the floor level, that we could identify the tilt and the direction. Actually, I've been spending literally days with one of my PhD students trying to develop a good measurement method for that, and it just did not work. That's the bad news. The good news is that we all know, not only in research but also in life, that we learn much more from failure than from success. So what we did is question another parameter for our channel model, namely, in general, it is supposed that the bare LED is exactly a Lambertian radiator with a certain order M. It seems that it's very sufficient for most models and characterizations, but the key question that we wanted to answer in this research is in fact a bare LED, commercial off-the-shelf bare LED, an exact, perfect Lambertian radiator? Question 1. And question 2, if not, what is the impact on the accuracy for received signal strength-based visible light positioning? Okay, we were fortunate enough that our colleagues sitting in the same building of the lighting and lighting laboratory They have a dedicated equipment to measure radiation patterns of light sources, and called a photogoniometer. And what we did, we selected an off-the-shelf LED that we were using for our indoor measurements, and we measured the radiation pattern. So on the right figure you have your LED, and the angle theta is defined as the inclination, if the skew angle, and the angle phi at the bottom is the planar angle with regard to a certain reference. And the rho is the radiation just at the observation plane below the LED, this distance. Now, what is the result of that measurement? The left figure at the full line, this is the perfect Lambertian radiation, and you can see that first of all, there's clearly a difference. So the dashed lines and the dotted lines are what we measured. And normally for Lambertian radiation you have perfect circular symmetry, rotational symmetry, which is clearly not the case. So for an angle phi 0 degrees, there is a difference with angle phi 90 degrees, as you can see. That's one thing. And the other thing, for very large angles theta, you can see that the difference with the Lambertian model becomes significant. The right-hand figure, we have taken a number of samples for different angles of theta, and you can see there's a small wobble in it. So it should be constant. Constant level would indicate rotational symmetry, but actually it is not. So that were the first signs that there's a significant deflection from the perfect Lambertian radiator. Now, without elaborating the equations in too much details, you can find it back in the paper. We ended up, it's not very difficult, it's no rocket science, we ended up with relationship of the relative error on the distance estimation. So the d hat is the estimation, the value that you estimate, the d is the ground truth. And in fact, it is the equation on your right-hand side, and it's clear that it only depends on the radiation pattern. So the equation can be used for different heights, which is very practical. For instance, if you install it into a warehouse of a ceiling of 6 meters high, or more in an office with 3.5 meters. So it's very practical for all kind of environments. This are a number of results. So on the left-hand side, you can see the epsilon, the relative error. So the figure indicates that for rho, meaning the planar distance or the distance in the observation plane smaller than a height, for instance, if the height is 5 meters, then the extreme right or the edge of the figure is 5 meters, where you can see that relative error varies between -2 and 0.25%. If you go larger, for instance 2 times h, then you can see you have a relative error between -2 and +2%. Now, a concrete example, suppose that you're at a ceiling of 4 meters high, then there you can see that the difference between the distance estimations and the true value, the ground truth, ranges between -10 and 1.5 centimeters, which is quite significant, especially considering the high precision that you have with visible light positioning, which is in the order of some millimeters. So the real bias is definitely introduced by the difference between perfect Lambertian radiator and a realistic radiation pattern. On the right-hand side, just as an illustration, you also see that the rotational symmetry is not respected. To conclude, knowledge of your exact radiation pattern is very important, but unfortunately it's expensive. You need the dedicated infrastructure, the photogoniometer. We have a single expression that can be obtained, that can be used for all kind of heights, whole variation of heights. Question is it interesting to develop a dedicated receive signal strength-based visible light positioning LED with a very well-known radiation pattern? That's an open question. What we are performing further research on is we just measured one LED. What we're going to do is take a larger number of LEDs from the same series and take a look at the variation that is introduced there. Also, what is typically done, first you have, for indoor positioning, you need at least 3 distance estimations, and then by means of trilateration you can find your position. Here we have only considered the error on the distance. So trilateration will most probably push the error, the bias down. And then last but not least, we are also considering using fingerprinting or application of artificial neural networks to obtain higher accuracy. So I think I'm well in time and would be glad to answer a lot of questions. Thank you.
Thank you.